Hi everyone, and thank you for listening to this recorded presentation for the EGU 2022. My name is Antoine Jacquey, and I'm a postdoc at Tufts University in the Department of Civil and Environmental Engineering. And today, together with my collaborator Robert Viesca, I'm going to show you some results on nucleation and arrest of aseismic fault slip during and after fluid pressurization. So the overarching goal of this work is to understand the coupling between fluids and fault slip, as fluid-induced fault slip can occur for natural fluid sources such as release of fluids due to metamorphic dehydration reactions at depth, which can lead to seismicity swarms, slow slip events or episodic tremors, but also for anthropogenic fluid sources with the injection of fluid in the subsurface in the context of geothermal energy, CO2 storage or wastewater disposal. There is a number of observations from the lab and the fields which showed that aseismic slip drives microseismicity and can potentially be seen as a precursor to seismic slip and major events. So that's why we're focusing here on aseismic slip. And there is a number of studies in the early 2000s by Serge Shapiro and his collaborators, which try to estimate the migration of microseismicity due to injection. So here as an example is sulfure microseismicity in a purely hydraulic perspective, even including a back front when injection was stopped. And here in this work we try to shift the focus from a hydraulic perspective to a mechanical perspective. And the goal here is to estimate the propagation of aseismic fault slip due to fluid injection. So here on the left you can see a sketch of an injection well and a pressurized region around the fault. And here on the right, during the injection, we can distinguish a fluid front, which controlled by diffusion, and a rupture front, which controls the extent of slip and microseismicity. And after we stop injection, we can still distinguish a rupture front, but also a locking front where the fault locks because of the drop of fluid pressure. So first I'm going to show you some results on the injection phase and later on the post-injection phase. So for the injection phase, there is a study by Bhattacharya and Viesca which showed that the relative position of the rupture front and the fluid front is controlled by a single parameter, which is called the fault stress parameter, which captures the fault stress criticality and the magnitude of the pressurization. And to summarize, for value of capital T close to 1, we have a marginally pressurized fault, meaning quite stable fault, and for value of T close to 0, we have critically stressed faults. And what they showed in this study is that if we look at the scaled amplification factor, which is the ratio of the rupture to the fluid front, and here is just scaled in a way that is bounded between 0 and 1. If it's bigger than 0.5, it means that the rupture front is ahead of the fluid front, and that happens for a low value of T, meaning that, and the other way around, for high value of T, we have the rupture front which is behind the fluid front. And so one of the conclusions of the study is that the rupture front is ahead of the fluid front for critically stressed faults. So we investigate the propagation of aseismic slip during and after pressurization based on numerical simulations. So here is a list of the assumptions that we follow for this model. So we consider a two-dimensional model with a one-dimensional fault, which is here horizontal. We model aseismic slip using a constant friction coefficient. And we consider injection directly on the fault plane with the fault having a constant fluid diffusivity. And furthermore, we consider that there is no leak-off between the faults and the surrounding elastic material. And finally, we consider uniform initial fluid pressure and stress distribution, which are captured by normal stress sigma naught and a shear stress tau naught. So the governing equation that we consider are the quasistatic stress equilibrium, which gives a distribution of normal stress and shear stress as a function of the distribution of the normal opening epsilon and the slip delta. The fluid pressure equation can be summarized into a one-dimensional diffusion equation based on the assumption that I mentioned before, and we account for slip as based on the frictional strength of the force, which is formulated here with a constant friction Mohr-Coulomb criterion. To account for slip, we follow an elastic plastic slip decomposition, meaning that we split the slip into an elastic and a plastic part, and we account for the plastic part based on the local incremental stress and relations. So we have which based on a thickness of the force and then on the stiffness. Here, just to mention, we consider that there is only plastic slip, meaning that there is no plastic normal opening, meaning that there is no dilation. So we benchmark our implementation based on the analytical solution given by Viesca in 2021 for constant fluid pressure fluid source, a constant pressure fluid source. And here we can see that the slip profile at 3 different times, so I think it's 1, 5 and 10 minutes after the beginning of injection. And what has been shown in this study by Viesca in 2021 is that the slip profile are self-similar during injection at constant pressure, meaning that they can all this profile can collapse into one with the proper scaling, and our numerical simulation in agreement with these results. So what happens after we stop injection? During injection, we have an analytical solution for the fluid pressure distribution and evolution. And after we stop injection, we can also estimate in a semi-analytical solution for the fluid pressure. And here on the right, you can see the profile of the fluid pressure in shades of blue during the injection phase, and in shades of red after we stop injection. So two things that we can notice. First is that in the surrounding of the previous injection point, we have a drop of fluid pressure, and let's say in a longer in a more far away situation, we can have an increase of fluid pressure after we stop injection, because we still diffuse the overpressure that we impose during the injection. So doing we can actually show that the evolution of the rupture front in wet and the locking front in wet, how they evolve over time during injection, so for T below 1 and after injection for T bigger than 1, scaled time since injection here. First thing we can notice is that the rupture front still propagates after we stop injection. So here as a comparison, in dotted black line I showed the evolution of the rupture front as if we didn't stop injection. So here we can see that we do not increase the rupture front as much as if injection would have continued, but we still increase to a given extent. The locking front evolves over time, propagating away from the previous injection point to the extent of the rupture, and when the locking front reaches the rupture front, then the fault stops to slip. One thing that we can notice is that there is still a significant actively slipping region after we stop injection, and that in turn we can show that there is also an increase of the aseismic moment after we stop injection. So what drives this slip rates after we stop injection? So here I show the profile of slip in dotted black lines at the end of the pressurization phase, and in solid black lines at a given time after injection shut-in, and in red the slip rate profile after injection shut-in. And what we discovered is that we can identify 3 different regions here. So the first one being the locking region, meaning that at the end of the injection phase this region was slipping, and after we stop injection at a given time this region is locked, and that is mostly controlled by a decrease of fluid pressure. So here is a Mohr-Coulomb profile same dotted black line at the end of the injection phase, solid black line after injection shut-in. So this locking occurs because of the drop of fluid pressure around the injection well. Second, we can identify a region which has uninterrupted sleep, meaning that it was sleeping during the injection and still sleeping after the injection. And here we can see that we have a slight increase of fluid pressure, but also a decrease of shear stress due to the frictional constraint. And finally, there is a region where sleep did not occur at the end of the injection and occurs now, so we still propagate, we extend the rupture after we stop injection, and here it's controlled mostly by an increase of fluid pressure as well, and this mechanism is quite similar to what happens during the injection. Okay, so we can look as well at the influence of the fault stress parameter, meaning the regional stress fields. And here in solid lines are the rupture fronts, and in dotted lines the locking fronts for different value of T of the force stress parameter. And something which is which you can see directly is that for marginally pressurized faults, meaning value of T close to 1, we almost do not extend the rupture at all during the post-injection phase. And oppositely, if we have critically stressed fault close to 1, we can more than double the size of the rupture. There is something, the locking front is not controlled only by the change of fluid pressure, because here we see that the force stress parameter has an influence on the evolution of the locking front. And we identified the limit of the evolution of the scaled locking front to the scaled time after injection, which is captured by the square roots for limits of T close to 1. So the message here is mostly that the locking front is not only controlled by fluid pressure change, but there is also some some process which are related to the mechanics. And finally, we can look at the arrest time and the influence of the force stress parameter. So first, we identify that the arrest time is proportional to the pressurization duration, and the arrest time can significantly vary based on the force stress parameter, meaning that if we have a marginally pressurized fault, so close to 1, the sleep will almost instantly arrest after we stop injection, and the other way around, sleep can continue for a really long time for critically stressed faults with value of T close to 0. Same is true for the rupture extent, so the final rupture length of sleep. We can see that for marginally pressurized faults, rupture will almost stay the same, and for critically stressed faults, we can more than double the rupture front for low value of T. So to summarize, so for the injection phase, mostly a recall from previous studies with a previous study. So sleep profiles are self-similar during pressurization at constant fluid pressure, and the force stress parameter controls the relative position of the rupture fronts with respect to the fluid fronts, with critically stressed with the rupture front being ahead of the fluid fronts for critically stressed faults. And after injection shut-in, we showed that the rupture front still propagates away from the previous injection point, and that the locking front is not only controlled by fluid pressure change, but there is also some aspects related to the mechanics. And the arrest time of sleep scales directly with pressurization duration, and that critically stressed faults will sleep for a longer time and have a larger final rupture than marginally pressurized faults. Thank you for watching this recorded presentation, and if you have any question, you can send me an email, or you can also meet me on Monday at EGU in Vienna. Thank you.